Folks, now it is time to jump into one of my favorite applications of circular motion and gravity. We're actually going to mix the two things we've been speaking about so far in this unit by talking about circular orbits. Let me give you a quick example. Obviously, we want to start there. Perhaps the most obvious example are satellites, both artificial and what we might call natural satellites orbiting the Earth. Here, from the simulation, this is meant to be the International Space Station orbiting around the Earth, and it does so in a circular pattern. Now, this only takes about 90 minutes to go all the way around. Yes, that's right. The astronauts that live on the International Space Station actually make an orbit once every approximately 90 minutes. Of course, one of Newton's big revelations was that not just the apple falls because of gravity, but the moon does as well. So here you can see a very similar thing here. For our purposes, we can assume that the moon goes in a circular orbit around the Earth. In fact, it's a little bit oblong. It's more like an ellipse, but almost exactly a circle. What's crazy about this is the scale that we're talking about. So if we go to the Earth-Moon system, this is what that looks like to scale. You can see the Earth is a small dot and the moon is an even tinier dot. More wild than that is if we get closer, you can see here, this is actually what it looks like for the International Space Station, or a typical low Earth orbit satellite to orbit the Earth. It is just barely above the surface. The important fact for us to understand, I'm going to slow this down a little bit, is that the thing that's keeping the satellite in orbit is actually the gravitational force. What's cool about this is you can actually turn gravity off. If gravity was turned off, guess what would happen to this satellite? Let me turn on its path. So it normally goes in a circular path. Gravity is the thing pulling it out of the straight line velocity that it has moment by moment. But if we happened to turn the gravity off, then it would just fly in a straight line. So the question is here, how hard is rocket science really? What I mean is, can we figure out things like what determines the path that a satellite will orbit? Like how long will it take? What will the distance between the planet and the satellite be? Let's see if we can investigate that, and we're actually going to use centripetal force to do so. So let's start by sketching out with our round object the planet Earth, and then we'll try to do as best we can to draw an orbit around it. I actually managed to find two circular objects, one for the Earth and one for the orbit. I'm going to try that. So I've drawn quite a bit here. I've got my planet. Let's give this mass of the planet MP. This can be Earth or whatever. It's got some radius RP for the radius of the planet. The satellite is orbiting in a circular orbit at a distance little r from the center. Very important to distinguish between the radius of whatever planet and the radius little r. Let's give the satellite a mass ms for mass of the satellite. And then finally, it's traveling at some horizontal speed, some linear speed at every moment as it travels around the Earth. So the question we want to answer is, what is the linear speed v of a satellite in a circular orbit around a planet? I mentioned this a moment ago, but in fact, satellites tend to orbit in ellipses, but you can make special circular orbits, and most of the artificial, or you might call them man-made satellites, but ones that humans have put up, tend to orbit in circles. Now, the beautiful thing about this is that we're going to solve this just like we solve every centripetal force question. Let's address that. Because it's moving in a circle, that is a dead giveaway. We're going to use centripetal force. This says add up all the forces acting on something moving in a circle, and that will give you the centripetal force, mv squared over r. Now this is really easy for this situation. As we saw in the little demo, there is a centripetal force, the force due to gravity, acting on the satellite at all times, and that happens no matter where it is in its orbit. So in fact, the only force, and we can just for completeness, the free body diagram on the satellite looks like this. It's just the force due to gravity. Now, to be clear, if the satellite was over here, the force of gravity would act inward like this, or down here, it would act upwards, and so on. So all we need to do is, in our equation, we're going to plug in the force due to gravity, which of course is just big G. We'll call that the first m the mass of the planet, the second m the mass of the satellite, and that's divided by the distance squared between them. That's going to be little r squared. And this side, the mass that we're talking about, the thing going in circular orbit, we're going to replace our just generic m. It's actually going to be the mass of the satellite. So it'll be m of the satellite, v of the satellite moving in a circular orbit. So we'll just replace that all over r. So when you recognize that this thing moving in a circle, its centripetal force is going to be the force due to gravity. That's just this thing here. The algebra is really easy. You'll notice that the mass is in both terms, the mass of the satellite. So we can actually go ahead and cancel that mass out. It drops right out of the equation. There's also a little r on the bottom on both sides. Now there's two of them here, r times r, so we'll cancel one of them and cancel that r there. A lot of stuff happened. Let's write down what it looks like now. You're going to have g times big M, the mass of the planet. I'm actually just going to simplify that and leave it as capital M. It doesn't have to be a planet, to be clear. It could be a sun or anything like that. Divided by r, we're going to keep that as little r, because remember it's the distance between the centers of the two things. And then on this side we just have, it's just v squared of the satellite. So to solve for the speed of the satellite, v sat, we just take the square root of both sides, and I'll switch it around. So we end up with the square root of big G times the mass of whatever the center object is, divided by the distance between them squared, and that's actually it. That is the definition, or that is the equation rather, for the speed of a satellite. Now, to do an example, because this equation on its own seems kind of benign, but let's do an example. Let's see how fast the International Space Station is going. For context, if you don't know much about the International Space Station, it was built by a bunch of countries, hence international. It started in the 1990s, and they've actually been adding more and more space shuttle, or space station rather, to it over the many, many years. This, for context in terms of size, is about the size of an American football field, or about the size of a soccer field. So this thing is really, really big. And if you go to my favorite website of all time, howmanypeopleareinspacerighttnow.com, the answer, 7. So 7 people are on this giant football field-sized object traveling around the Earth at some speed which we are about to calculate. So what we want to know is, what is the linear speed, or the speed at any moment along the way, of the International Space Station? To find that out, we're going to use this equation. We're going to need the mass of the Earth, which is 5.997 times 10 to the 24 kilograms. We're going to need big G, which is 6.67 times 10 to the minus 11 meters cubed per kilogram second squared. And then the other thing we need is little r. Now that's a little bit tricky. So little r is going to be the radius of the Earth plus however high above the Earth the International Space Station is. So this picture is actually a little bit more accurate in terms of scale. We have, again, we can look up the radius of the Earth. We also need to look up the height here that the International Space Station is above the surface. So let's look that. So you got to be careful when you look this up. I first looked it up and it gave it to me in miles, then in kilometers. We end up needing this in meters. So the height of the International Space Station above the surface is 408,000 meters. So we will use that for our calculation. So here we've got our data. Again, the mass of the Earth, the radius of the Earth in meters, the height of the International Space Station in meters, and then big G. I just want to very quickly point out what H means in this context. So again, R is the total distance, the little r. Big R is the radius of the Earth, which is a number we wrote down. And then this distance, I'm going to add in a different color. Let's do green. So it should stop right there. Sorry about that. So that right here is the height that we just looked up. So none of this is to scale. I did a very poor job of drawing this. Here, this is the height of the International Space Station, the ISS, International Space Station. So with all of that, let's go ahead and actually use our equation. The speed of a satellite is square root big G m over r. So we'll just plug that in, 6.67 times 10 to the minus 11. What was the unit? Sorry, meters cubed divided by kilograms seconds squared times the mass of the Earth. 5.97 times 10 to the 24 kilograms, all on top. And then on the bottom, this little r is going to be the radius of the Earth, which I've got right there. It's also stored in my calculator, plus 408,000 meters, and that all needs to get square rooted. So right now, more than ever, is one of the reasons to plug these into your calculator if you have the ability to. If not, you can simply plug those in. I got lazy. This should be that 6.37 times 10 to the 6th. You get an amazing 7664. So V of the satellite is 7664, well, close enough, meters per second. I want to give you some context for that number. That is so fast. That is let's call it 7.7 kilometers per second. So scholars from Riverside's campus to the Circle downtown, that is approximately 7.5 kilometers, it's about 4 miles. So that means that the people, all 7 of them, at least when I recorded this video, that are on the International Space Station every moment of every day are going 7.7 kilometers every single second in orbit around the Earth. So fast. So perhaps the next obvious question is, if they're going 5 miles per second, 4 or 5 miles per second, 7.7 kilometers per second, how long does it take the folks on the space station to go around? I may have already spoiled that, but let's see if we can figure it out. Let's see how long it takes for them to go around once. Let's see what this simulation tells us. Approximately 90 minutes, maybe about 100 minutes to go around. Let's see if we can work that out ourselves. So the place to start is right here with the speed of the satellite. The speed of the satellite is, again, square root G big M over R. We can remind ourselves that the speed of something moving in a circle is 2 pi r over t. T is what we're interested in. T is the orbital period, or in other words, how long does it take the International Space Station, or any satellite, in fact, to go all the way around. So this requires a decent bit of algebra, but let's go ahead and jump right in. Let's replace the speed of the satellite with this equation. So this will be 2 pi r all over capital T. This is G m over r. Now there's a couple different ways you can do this because we've got that square root in there. We've got lots of ways we can write it. But what I'm going to do to combine the r's and clean this up is we're going to end up squaring both sides of the equation. So if I square this side, I end up with 4 pi squared, r squared, all over t squared. I've just squared both sides. I'll indicate that here. The reason we want to do that is that cleans up this side quite a bit. Okay. Now we can do some moving around. Let's go ahead and move the r's together. So multiply both sides by r. We'll end up with 4 pi squared r cubed. Let's do a bunch of moves here at once. Let's move the t squareds up. T squared. And at the same time, let's move the g and the m down to the bottom. Nice. So this is kind of interesting. Let's swap sides here, and I'm going to write this in kind of a funny way. So the period squared is equal to, I'm going to put all these constants out in front. So this is sometimes referred to as Kepler's third law. This says that the period, the time it takes to go around the sun, for example, is, that period squared is proportional to the distance between the sun and the object to the third power. Sometimes you'll see that written t squared is proportional to the radius or the semi-major axis, I'll write it properly, cubed. Now the short version of what that means is that the farther away you are, the longer it takes to orbit. So whereas the time for the Earth to go around once is, 1 year, the time that it takes for Jupiter is around 5 years. And if you keep going out farther, the time for Saturn is around, I believe it's 12 years, and so on as you go farther and farther out. So several things. I've relisted the data from just a moment ago for the International Space Station. We're going to put this in a box because this is important. This is Kepler's third law. But now let's actually do our job here. Let's see if we can find the period, the orbital period of the International Space Station. So that would just be this, but take the square root of both sides. So 4 pi squared all over gm. And then I'm going to write this in a funny way. This little r, if I can remind you, is the radius of the planet. So the radius of the Earth plus the height. The radius plus the height. So we'll put the radius of the Earth plus the height of the ISS. Now, this is perhaps the most challenging thing you've ever plugged into your calculator as a high school student. This is really easy to goof up. So let me try to show you what that should look like in your calculator, and let's get our answer out in seconds. So you want to be super careful here. You need to make sure you square the pi. You put the r, the radius of the Earth, plus the height of the International Space Station. We need to raise that to the third power to cube it. And then we need to make sure that we're dividing by both g and m together. If you don't put those parentheses, it's going to think you want to divide by g and then multiply by m. Anyway, once you hit return, you should get some large number of seconds. So this would be the orbital period of the International Space Station is 5,556 seconds. Let's get lazy and just look that up. That's something like 93-ish, 92 and a half minutes. So this is 92.5 minutes. That's crazy, people. That means that during one class period at ICS, during the normal course of the year, which is approximately 90 minutes, the International Space Station will have gone almost the entire distance around the Earth. Think about that. The fastest flight you can get on to take you around the world, like from here to China, takes like 12 to 15 hours. And these folks can do it in an hour and a half. Insane. So we've covered a lot about circular motion, circular orbits. That is by no means all of it, but that is what you all need to know for right now. Thanks so much.